Okay guys, so I'm going to go through a video here helping you guys out with problems like yours. Now this is your worksheet, but once again, I'm not going to be doing your problems. I'm going to be doing problems like your problems, and it's going to be your job to solve and answer these. And please do make sure you bubble in your final answers on the bubble sheet and then submit those to me electronically. That should take care of things. So let's go ahead and get started here. I'm going to do the teacher example one. Now each one of my problems are just like the ones that you guys are going to have to do. Once again, I caution you guys, I can only give you guys so much. I'm not going to try to overwhelm you, but you do need to be doing more practice than this if you can. It would be a wise choice. So we're going to start off with some derivative reviews. Okay, so we have y equals negative 5 over 3x. Now I'm going to rewrite it like this really quick. This is not a necessary step, but I just want to get that x away from that fraction. Now the next thing I'm going to do is I'm going to rewrite it like this. Instead of having it as 1 over x, I'm going to change that to x to the negative 1 power. That makes it really easy for me to apply my power rule whenever I find the derivative. So the derivative then, and what they're actually asking for, is what you get when you take this power and you multiply it to the front. So that's going to change it to a positive 5/3. And then we're also going to subtract 1 from that number on the top, and we end up with negative 2. Now they could leave the answer like this, but it's also very possible that the answer will be written like this, putting the x squared on the bottom. Okay, so that's how we do a derivative in that case. Let's go ahead and take a look at another question here. What about whenever you have square roots, or cube roots in this case? So once again, we want to start off by rewriting the problem. I'm going to change that to an x to the, that x has a power of 1 on it, but it has a cube root on it also. The root goes in the denominator and the power goes in the numerator. So we're going to change that to a 1/3 power. Now the next thing we're going to do is just apply our power rule. So if I want to take the derivative, I'm going to take this guy, I'm going to multiply it to the front. This time I'll actually show my work. And we also want to take 1 away from that, which is going to make it become negative 2/3. Okay? In this case, the 3's are going to cancel when we multiply those two fractions in the front together. And so y prime is equal to 1/2 x to the negative 2/3. Now they may leave their answer like that, but another way that that answer can be written is like this. Okay, so the negative can move this x to the denominator. The 3 in the denominator can be rewritten as a cube, and the 2 in the numerator can be written as a power on the x. So just be aware of the different ways that that problem can be expressed. Let's go on to an example for number 3. Now example 3 has a couple things going on in it. It has natural log, it has chain rule, but most importantly what I want you guys to notice is it has a product. We have two functions that are being multiplied together. Okay. When I taught this, I think I called one A and I called one B. And so when you take the derivative, the product rule works like this, where you're going to have AB. Take the derivative of one in the first set, but the derivative of the other in the other set. Okay, so the derivative of A, let's go ahead and find that. Well, the derivative of ln is always going to be 1 over whatever's inside. But we also have to take the derivative of the inside function, which is 2. And so those cancel, and I'm left with 1 over x for my derivative of A. Taking the derivative, actually, for the next part, we just put b there. It's just going to be cosine of 5x squared. We don't do the derivative. Now for the next set, a stays the same, so it's just going to be ln of 2x. But we are going to take the derivative of cosine. So the derivative of the outside function, which is cosine, is negative sine x. Now they're not going to put a minus in between the ln and sine, because that's going to make it look like a minus sign, and it's not. What they're going to end up doing is putting that minus in the front. there now as a placeholder. Plus then. Also, we need to take the derivative of the inside, which is going to be 10x. So this is really ugly. So let me rewrite this in a much prettier fashion for you guys to see it a little better. We have 1 over x cosine of 5x squared minus 10x ln of x, 2x, sine of 5x squared. So we had a lot going on there. We had power rule, we had product rule, we had derivatives of logs, and we had derivatives of trig functions, all kinds of things. So a lot going on in that particular problem. Let's move on to another one here. So this one's main point is to demonstrate the quotient rule. So you guys, I think you guys all remember that one pretty good, actually. Before I begin, though, I want to go ahead and just find the derivative of these two things separately. So the derivative of the top there, well, when you take the derivative of any e function, it just stays the same. It doesn't change. However, in this case, we have an inside function, a 2x squared there. So you're going to multiply that to the front. So the derivative of the inside multiplied by the derivative of the outside there. So that's the derivative of the top. The derivative of the bottom is pretty simple. That's just 15x squared. So what we're going to do is we're going to do our quotient rule. The quotient rule is low d high. The derivative of the top is this. Minus high d low. Draw a line and square below. And we could probably clean this up a little bit. The 2x and the 5x cubed can be put together to make 10x to the 4th. Let's see, what else? The 15x squared would probably come up to the front here. And the bottom can be rewritten as 25x to the 6th. Now, you know, how much do they want you to simplify this? Well, I really don't know. It depends on the problem. This thing, though, can be simplified more. If you look at the top really quick, what can we factor out of each of these terms? Well, they both have an e to the x squared power, right? But they also have x's in common, and both 10 and 15 have a common factor as well. So what we can do is we could take out a greatest common factor on the top. 10 and 15 can both be divided by 5. We could take out at least an x squared out of both, and we can also take the e to the x squared out of both. So if I take 5x squared, e to the x squared out of this, dividing the 10 by the 5 would leave me with 2. Dividing x to the 4th by x squared would leave me with x squared, and there is no longer an e to the x squared in there anymore. Minus dividing 15 by the 5 that we're factoring out would leave me with 3. Taking out the x squared means there is no more x squared, and taking out the e to the x squared means there's no more x squared. And then the bottom looks like this still. We haven't done anything different there. Now that we've done that, we can actually reduce a little bit as well. Let me clean up my screen a little bit. Now, I don't know if your problem is going to be quite this difficult to simplify or not, but can't hurt to see how to do it, I guess. All right, so I can reduce the 5x squared with the 25x to the 6th there. 5 goes into 25 5 times, and x squared goes into x to the 6th, x to the 4th times. So the bottom reduces to that, and the top completely goes away. And so on the top now, I'm just left with the e to the x squared on the outside, and a 2x squared minus 3 on the inside. I'd say that's probably the most simplified we're going to get for that quotient rule derivative. Okay. Moving on to our next question. Just a basic chain rule trig derivative. You guys need to be memorizing those trig derivatives. The derivative of the outside multiplied by the derivative of the inside, right? So the derivative of the outside is secant tangent. The derivative of the inside is 6x squared. Pretty simple, not too bad. Just got to remember the rule, though, about what the derivative of secant is. Tangent. Likewise, you need to be taking the derivative of all the trig functions. And once again, I'm not going to give all of them to you on these worksheets. Too much work to do in too little time. But you should be practicing as many as you have time to practice and memorizing them with those flashcards that I posted for you guys a while back. All right. We're also looking at some arc trig derivatives here. All right, so there's probably about 3 good arc trig derivatives, or 6 of them, that you need to memorize and be ready to use. So the derivative of, you don't need to write this part really, but the derivative of cosecant, arc cosecant I should say, has a formula. The formula looks like this. It's 1 over the absolute value of whatever's on the inside. Actually, it's negative 1 over the absolute value of whatever's on the inside times the square root of the inside squared minus 1. So that's the formula for the derivative of our cosecant. However, in this case, this is a chain rule. Also, we have the derivative of the inside. So what will this look like? Well, this is just a formula. So let's go ahead and apply that formula to this actual problem now. So it's going to be negative 1 over the absolute value of the inside times the square root of the inside thing being squared. So that would be 25x to the 4th minus 1. But it's a chain rule, so we also need to multiply it by the derivative of the inside, which is negative 10x. And so what they're going to end up doing is multiplying those two things together that you see on the top there and putting them together to be a positive 10x. Now, I'm pretty sure on the software that I'm using, they're going to leave the answer like this. However, sometimes you can simplify this a little bit more. Like, the absolute value of negative 5x squared is just going to be positive 5x squared. And then 10x over 5x squared can be reduced. So 5 is going to go into 10 twice, right? And then the x is going to go into the x squared once, leaving you just x on the bottom. But I'm pretty sure, like I said, they're going to be leaving the problem like this. Back up a little bit. And I lost it, but oh well. Let's go ahead and proceed on to the next question here. All right, number 7, another arc trig function. So the derivative with respect to x of cotangent, what is that little formula going to look like? Well, the derivative of arctangent is negative 1 over whatever is on the inside being squared, and it's plus 1, okay? So in this case, it's going to be negative 1 over the inside squared, so that's 9x to the 6th, plus 1, multiplied by the derivative of the inside, which is 9x squared. And so, once again, they're going to multiply the 9x squared times the negative 1, and they're going to make it become negative 9x squared. Okay? So once again, you got to take the time to memorize those. Okay, number 8. Oh boy, implicit differentiation. All right, so what implicit differentiation means is you have an equation that has x's and y's in it. And so what we want to do is we want to find the derivative of this thing. We want to find y prime, which is just short for saying dy dx. So the way that we're going to do that is we want to find the derivative of this whole thing with respect to x. Okay? So we're going to go ahead and distribute this. So what's the derivative of 1? Well, the derivative of 1 is 0. Next, we're going to take the derivative of 2x with respect to x. That's just 2. Minus, and now we get into some interesting stuff. There's a couple of things going on here. First of all, put some parentheses here. It's going to be a product rule, you guys. There's two things being multiplied together. So I'm going to call the 5x cubed my a, and I'm going to call the y my b. So we have ab plus ab derivative of one, derivative of the other, right? Just like we did back in question. So the derivative of a is pretty simple. The derivative of 5x cubed with respect to x is 15x squared. And we don't change the y in this case, we just put it there. Now we're going to put a, 5x cubed, but we are going to find the derivative of y. Now when you take the derivative of y with respect to x, what you're going to do is you're going to take the derivative of y like you would do if you were taking the derivative of x. And the derivative of x would be 1, right? So the same thing here with y. If you take the derivative of y, you just get 1, but you get a y prime out of it as well. Anytime you're taking the derivative of a letter that doesn't match the denominator, you're going to put a prime next to it as well. You multiply by a prime. It's like a chain rule, something we learned a little while back. Okay? At this point now, what we want to do is we want to find what is y prime. Okay? Well, we found the derivative with respect to x, but we haven't figured out what y prime is yet. In order to do that, I want to get y prime by itself. So the first thing I'm going to do is I'm going to distribute that negative through. I don't know if you'll have to do this on your problem or not, but the next thing you're going to want to do is you're going to want to take all these terms here and you're going to want to move them to the other side. So I'm going to subtract the 2 to the other side. I'm going to add the 15x squared to the other side and cancel them off of this side. The next thing I'm going to do is, since this negative 5x cubed is being multiplied with the y prime, I'm going to divide both sides by negative 5x cubed. So if I do that, this cancels. And then I'll also put it over here underneath of this one, but I'm running out of screen space, so I'll show my work up here. So now I've got negative 2 plus 15x squared over negative 5x cubed prime. So before I go any further, I want to make sure you guys got this. So we take the derivative of the whole thing with respect to x. And anytime you take the derivative of something with a y, you take the derivative like normal, but don't forget to multiply it by a y prime. After that, you get the y prime by itself. Now, there may be some simplification that needs to happen. I wouldn't be surprised if they, instead of having a negative in the bottom there, I wouldn't be surprised if they just changed the signs of everything and rewrote it like this. Because it's not kosher mathematically usually to leave negatives on the bottom if you don't have to. So there's that. I'm kind of curious to see how the answer is being written here, so I'm going to bring up the answer key for this one and see what they put. Yeah, they got rid of the negative on the bottom, and I think I also just realized I left something out. What did I leave out? Here it is. When I moved this piece here on this problem, it should have been a y here, so I left a y off of the problem. Oopsie doopsie. Anyway, there it is. So take the derivative of everything with respect to x, but anywhere we have a y, multiply that by a y prime once you take the derivative of it. Get the y prime by itself and simplify if necessary. That's called implicit differentiation. All right, moving on to number 9. This is another thing. It's kind of like, gosh, I don't know. They'll probably, it's not a huge likelihood you're going to see one of these on your exam, especially now since they're just doing free responses, but it is possible. I would say if you had the multiple choices, you'll definitely see one. It could pop up on a free response. I'm not going to say I haven't seen these, but definitely something you want to put on a flashcard and review. Can't hurt. So here's the deal. They want us to find f inverse prime of 9. Now there's a formula for that. F inverse prime of 9 has a formula. The formula for any inverse function derivative is going to be 1 over f prime of f inverse of whatever your input is. In this case, it's 9. Okay? So there's that. Now, here's what we're going to do. We're going to work our way from the inside out. So the first step you guys got to do is memorize that formula. The derivative of an inverse is 1 over the derivative of a regular function with the inverse value plugged into it, right? Now, we're going to work our way from the inside out. So the first thing we're going to do is we're going to find out what this is. And that's where this piece comes in handy. If f of negative 2 equals 9, then f inverse of 9 equals 2. They're just flip-flops of each other. So this becomes 1 over f prime of 2. And now what I'm going to do is I'm going to come back up here to f. I'm going to find f prime, and then I'm going to plug in 2. So f prime of 2 is going to be, if I take the derivative of that, I get 4x, and the derivative of that, I get 1. And we're going to plug in 2 to that, right? And we get 7. And so this ends up being 1 over 7. Right? So that's the formula for the derivative of an inverse function. And basically all it's saying is that the slope of an inverse function at one value is the reciprocal of its original function at its opposite input value. So let's go ahead and move on there to new things. Now we get to move on to some integration. We're going to leave derivatives behind now. All right, so we got to switch our brains around for this because it's the opposite way of thinking. All right, so in this particular problem here for number 10, we have all kinds of applications of the power rule. Well, the first one's basic. I'm going to leave that one alone for now. It's just going to be the integral of 15x to the fourth. That's not going to change. But the other two, anytime you want to use the power rule, you want to rewrite it. So I'm going to rewrite the fraction separately, 4/3, and I'm going to change that cube root of x into x to the 1/3. And for this guy here, 20 is going to stay where it is, but I'm going to change that x to the 5th to x to the negative 5th as I move it to the numerator. And now I can apply the power rule. And the power rule works like this. You add 1 to the power, and you divide by that new number you just created. And we're going to repeat that process. So now for the next one, if I add 1 to this power, I'm going to end up with 4/3. And then I'm going to divide by 4/3. Now, what we talked about earlier was that instead of dividing by a fraction, that's the same thing as multiplying by its reciprocal. So that's ringing a bell a little bit. So instead of dividing by 4/3, we're going to multiply by the reciprocal. That's the same thing. Plus, add 1 to this power, and divide by that new value. Okay? So final answer would look something like this then. 5 goes into 15 3 times. Everything cancels here, so we're just left with x to the 4/3 power. And then 20 divided by -4 is going to be -5. And it's hard to say if they're going to leave it like this or not. They might choose to put x to the 4th on the bottom as a positive now. Don't forget your plus c also. I'm running out of space. I'm going to bend my answer down there a little bit. But yes, when you integrate, you always get a plus c to account for any constants that would go away if you were to take the derivative. All right, let's go ahead and move on to another question. All right, so this problem that I included here for number 11 is just to remind you of the good old U substitution. So U substitution means you look for the inside function, usually, and it's the function whose derivative will help cancel out an extra term. So what we do now is we get the dx by itself by dividing both sides by 4x to the 3rd and multiplying both sides by dx. and then we do our u sub. So we have 20x to the third. This piece here was our u, and the dx is going to be replaced with du over 4x cubed. And what should happen if we did our u sub correctly is the x cubed should go away. We are left with some extra numbers, but that's not a big deal. 4 goes into 25 times. So here's a nice simplified way of writing this. By the way, anytime you have a constant, you can just kind of push it to the outside of the integral. You don't have it in there. You don't have to push it out to the front, but you can. What you're not allowed to do is you're not allowed to push variables out of the integral. Those are affected by the integration process, whereas constants are not. Okay, so now we're going to go ahead and take the integral of this. So we're going to add 1 to the power, and we're going to divide by that value. Don't forget 5 that was on the outside, and don't forget plus c. And at the very end, you should go back, unless you're doing a definite integral, you should go back and replace the u once again. And so your final answer for this would be 5 over 6 parentheses x to the 4th plus 2 to the 6th power plus c. All right. Next question. So this is another u sub problem, but in this case we have some trigonometry involved. So once again, here's my inside function. We're going to take the derivative of that. It's supposed to be a u. So the derivative of e to the x, e to the 3x is just e to the 3x, but we need to multiply it by the derivative of its power, which is 3. The 2 just goes away when you take the derivative. Next, we're going to get the dx by itself. We do our u sub. Negative 6 e to the 3x will stay there for now. Then we're going to have secant squared of u, and we're going to replace the dx with du over 3e to the 3x. So the e to the 3x's go away. 3 goes into negative 6, negative 2 times, which I'm going to push to the outside, and now we're left with this. So once you get done with u sub, you should have nothing but u's left, no more x's. All right, well, it turns out that the integral of secant squared is actually a very nice integral. It just so happens to be tangent. Don't forget c. And at the end, unless you're doing a definite integral, which we're not, you're going to go ahead and replace your u once again. Okay, so that one. Moving on. All right, so this problem and the one after, no, I guess not the one after it, but some of these problems you just kind of got to recognize, and once again, that's where your flashcards come in helpful. Let me help you out here a little bit. We had a formula that we memorized a while back. It looked something like this. And what it was an arc function. It was arc secant. Okay, so now it's a little bit trickier than that actually. I just remembered we're going to put an a here also, and it's going to be squared. And let me adjust this a little bit. I just realized it's a little bit more complicated than derivative. Working backwards usually is. What it would turn out to be is it would turn out to be 1 over a arc secant of the u over a. I believe it's usually going to be an absolute value there. So there you go. So how it works then is basically we're going to take the square root of both of these things here and put them in there. But This is a little bit different because it's also a U-sub problem. So the way that the arc secants work is you always need a square here. You can't have a sixth power. So the first thing I'm going to do is I'm going to rewrite this as a square. So what number to the second power would give me this? Well, that would be 4x to the third. Just so you know, spoiler alert, a lot of times it's just going to be what's out there. And so what that tells me is that's going to be my u for a u-sub problem. Okay, so the derivative of that with respect to x is going to be 12x squared, which means that dx is going to be equal to du over 12x squared. So if I wanted to rewrite this integral now, here's how it would look. We have 12x squared over, that's a u, isn't it? U is 4x cubed, so I'm going to put a u right there. And then we have another u minus 4. We're also going to replace the dx, which I should have written earlier, with du over 12x squared. And the 12x squares just go away. And lo and behold, we have our little formula here for arc secant. Now remember, there's a slightly different one for arc tangent. There's a slightly different one for arc sine. You have to just get those flashcards and memorize them. I didn't include all of them on this study guide just because I don't want to overwhelm you with time, but you do need to have those memorized. I'm just kind of giving you a little taste of everything to let you know what you're studying for. Now we're not quite done yet. Let's go ahead and do the integral. So I've gotten it to a place where it fits the pattern of the arc trig function, and here's how it works. It's going to be 1 over the square root of this number, and then it's arc secant for this particular format, and it's going to be the absolute value of u over the square root of 4, which is 2 again. And once again, you don't want to forget your plus c, and you want to replace your u with what u equals. U was 4x cubed, right? So we have 1 over 2 arc secant of the absolute value of 4x cubed over 2 plus c. And just as an extra little note to you, a couple of things. They could write it like this. That's also how you can write arc secant, is with a secant with a little -1 there. Another little note to be aware of is that since this one has an odd power on it, we have to leave the absolute value sign. But if this was an even number, there's no point in having the absolute value signs, and you could even reduce the fraction also. But in this case, we're just going to go ahead and leave it like this. Okay? All right, moving along, getting there. All right. This is a unique situation, not very common. Once again, not likely to see it on your AP test this year, but it's possible. So I thought we'd review it. Anytime you have a denominator that's a trinomial, there's a really big possibility you're going to use this strategy, which is a strategy known as completing the square. What does it mean to complete the square? Well, I'll show you. Completing the square means that we want to turn this into a perfect square trinomial. What is a perfect square trinomial? Well, a perfect square trinomial is one such that when you factor it, you end up with x plus or minus something squared. Now, that's not what this is going to be. If you factored that, I'm not even sure if that is factorable or not, but if you did, you're probably not going to get a perfect squared binomial there. So what we're going to do then is we're going to make it become one. And the way you do that is by adding the right number in there. But to keep it kosher, we're also going to subtract that number just so it doesn't change the value. But at least this piece here will now be a perfect square trinomial. Now, how do you do that? You take half of this number, which is 2, negative 2, and then you square it, which is a positive 4, and you put it there. And don't be deceived. It's not always going to be like, oh, well, if this is 4, this is 4. That's not how it works. This is a coincidence. How you find it is you half the middle number and you square it, and that's what goes there. And it just so happens now that whenever you factor this one, it is a perfect square. It is x minus 2 squared. However, remember, if I add 4, we also get to subtract 4. Because if you don't subtract the 4, then what you did was you changed what it equaled. But if we add and subtract 4, it's kind of like those 4's cancel out, so they don't really matter. But we have changed the way it looks. So here's what this final thing would come out to be here. It would be x minus 2 squared plus 16 once you combine those. Okay, so that's the basic strategy there. So when you have a trinomial in the bottom, the first thing that you're going to do is you're going to complete the square on the bottom. And what we just found out that is it's x minus 2 squared plus 16. Now once you have that, hopefully you would be recognizing, if you've been using your flashcards, that that's an arctangent rule. Arctangent looks like this. It's two squares being added together. And so what we have here is we have two perfect squares being added together. So to kind of clean this thing up a little bit, we're going to do some u subs. So instead of having an x minus 2, I want a u. So I'm going to do u equals x minus 2. The derivative of u with respect to x is 1, which means that du equals dx. And so now we can rewrite our integral like this. First of all, I'm going to put the 7 on the outside. We don't really need that there. We're going to replace the x minus 2 with u. And we're going to replace the dx with just du now. And now you can see how it looks a heck of a lot more like an arctangent problem. And the way we do this is the a is the square root of this number, and the u is the square root of this number. So we have 7 arctangent, which can be written as tangent with a little negative 1. And it's going to be u over 4. Oh, and I forgot to put 1 over a in the front as well. So the square root of that is 4, right? So we should also have an over 4 in the front, plus c. And then finally, we go back and replace the u once again with what u equaled originally. So that's a strategy that involves completing the square, and you use that anytime you see a trinomial in the bottom. And when you have completed the square, it's almost always going to turn out to be an arctangent problem. Think of another situation where that would apply. All right, as for number 15, almost every problem we've looked at, I don't know if you guys have noticed this, but every problem that had a fraction involved, like these things, the top is always just a single thing, but in this case it's 2. And whenever you have 2, the strategy that you're going to employ is you're going to split the numerator. Now you can only do this if you can only split a numerator up. You can't split a denominator up. It doesn't work like this. But the way we can do this is you could just do this one over the denominator plus this one over the denominator. That's it. And then what we could do from there is we can kind of reduce this a little bit. This would turn out to be x over 5 if you reduced that fraction. And if you reduce this fraction, you get 7/5. And now we can just kind of take the integral just like we normally would. I'm going to rewrite it a little bit though so it looks more friendly. So instead of x over 5, I'm going to put 1/5 x. And from there, you just do your derivatives like you normally, or your integrals like you normally would. Power is 1. So I'm going to add 1 to the power, which is going to make it 2. And I'm going to divide by 2, which if you divide by 2, that's just going to multiply the bottom by 2, which is going to make it 10. Plus, when you take the integral of a constant, you just put an x next to it, and don't forget your c. And what else do we have? Definite integrals. Now, definite integrals means you're going to take the integral and you're going to plug in the numbers to actually find a value. Usually what it represents is like an area under the curve. It also represents change or anything like that. But anyway, I digress. So first of all, once again, you've got to know your integral rules. That's an arc sine. Arc sine looks like, comes from this rule. 1 over square root of a squared minus u squared. Okay? So, in this case, the number that goes here is the square root of that, and the number that goes here is the square root of that, and pretty much ready to go. So the integral of this is pretty simple. It's going to be arc sine, and we have the integral of, we take the square root of that, that's the numerator. Take the square root of that, that's the denominator. And we don't put a plus c when we do definite integrals, right? My limits now are this. So remember, after you do an integral, the integral sign goes away, and you change it into brackets, right? So notice I've got that now. And then we put the limits on the right side corners of the bracket. So now what we're going to do is we're going to go ahead and plug these numbers in, okay? So I'm going to plug in this. And then we're going to plug in the bottom number as well and subtract it. That's how you do definite integrals. So after you take the integral, you just plug each one in and subtract those two answers, right? Okay, the next thing we're going to do is we're going to simplify these complex fractions here using whatever strategy you feel comfortable with. One way you could, I don't know, the way that I shared with you guys how to do it in class is a little complicated, but the way I can do it now in my mind is a little bit easier, but the problem is that doesn't always work. So that's why I didn't teach it. But the way I showed you guys in class was I said multiply the top and the bottom by the little denominator, so the little denominator goes away. And so now the bottom is 3 times 2, and the top is 3 radical 3, and then the 3's cancel. And so what you're left with then is a radical 3 on the top and a 2 on the bottom. Same thing here. Multiply the top and the bottom by 2. The 2's cancel, and then the 3's cancel. So I'm left with nothing on the top, but that really means there's a 1 there, and then 2. Have that. And this is where things get fun also. You guys got to remember your unit circles. It's hard to say. Since this is an FRQ test, you guys, honestly, stop right there. There's really no need to go further. So, if you needed to do a problem like this on your FRQ test, which is what your AP test this year is, literally just stop here. Don't try to go further, because I know that most of you guys are extremely weak in that area, and this is a full credit answer. However, for your multiple choice problems you guys are working on, this is not good enough, and I do want you guys to know how to do it anyway. So we're going to do it, but on your FRQ, please stop there this year. Don't try to go further. All right, well, first of all, I want you guys to know this, that sine of theta equals, we'll just say y, okay? So if sine of theta equals y, then arc sine of y equals theta. And my point in telling you this is that the y coordinate is what you get whenever you plug an angle into sine. Okay, so in this case, what that means is this is the y coordinate. And what we want to know is what's the angle that goes with that. Another thing you have to remember is that sine is only concerned with this side of the unit circle. It goes from negative pi over 2 to positive pi over 2. Now, where is radical 3 over 2? Well, that's way up here at the top. And that's going to be at pi over 3. So arc sine of radical 3 over 2 is pi over 3. Arc sine of a half, that happens right here, and that's at pi over 6. So getting a common denominator, multiplying the top and bottom by 2, we end up with our final answer of pi over 6 there, if we actually do the subtraction. But once again, just stop there on your FRQ, but for your little worksheet that you're working on this week, go all the way out for that. All right, moving on. And it looks like that's all I gave you guys for this week. So, well, hopefully that's helpful to you guys. And once again, I highly encourage you guys to be expanding your horizons here. Once again, I mean, I've only done one definite integral problem. I've only done, specific types of problems that involve secants and trig and arc trig functions and all that. So definitely want to be looking up on Khan Academy and College Board and messing around with various other types of problems from your notes this year and using the flashcards if you want to be ready for that exam. But anyway, hope you guys are doing well. Hope that wasn't too overwhelming for your first week back, and we'll stay in touch.